Hello and welcome to the Brain and Transcranial Photobiomodulation Virtual Summit. I'm your host, Dr. Joe Doduro. My guest is Dr. Daniel Bourassa. He's a chiropractic physician and researcher, educator with over 35 years of clinical and patient experience. He holds a PhD in biomedical sciences, and he's very, biomedical research of transcranial laser therapy is really his high point. He's going to examine for us some of the quantum aspects of photobiomodulation, photobiostimulation. Thanks a lot for joining us today, Dr. Dan.
Good to talk with you, Joe.
Now, you have a very, you were a chiropractor, which is like physical medicine, and then you got a PhD, and you kind of focused on lasers and light and energy. I mean, it seems like it's a kind of divergent. Well, how did you start to use lasers in your practice and in your mindset?
Well, actually, I began using lasers in the very early 2000s, 2001, 2002. I started off with the class 3B. It was affordable at the time, using it in neuromusculoskeletal practice. I was involved in at the time, what ended up being, it was orthomolecular medicine, became functional medicine, and working with medical doctors, did various things and did the research, review of literature, and tried some things. I went to medical school in a Caribbean medical school, and also obtained the PhD in biomedical science. Back in 2010, I did a paper with a medical doctor on the use of lipolaser and its effect on body fat reduction or body contouring. And actually, the manufacturers there were telling the doctors to do it wrong. So it actually was detrimental to the application. We changed that because they just didn't understand the laser physics and what they were doing in delivering energy into the fat cells. They actually were overstimulating the fat cells, I believe. And when we reduced the time down to appropriate for the type of lasers that we were using, we improved the results by about three times. And so I still am using those today and offering that with pretty decent results. But getting back more into the transcranial brain stuff, in 2015, I became very interested in its use. Henderson and Morris did a study on the penetration of class 3 and class 4 lasers. And so I really started looking at that because, we had a lot of people. I'm in Pensacola, we have military. There's a lot of post-traumatic stress syndrome. There's obviously everybody is depressed now, given the amount of medications that are on there. And people that had, cognitive decline need to have something potentially more efficacious of the type of therapy for Alzheimer's and that sort of thing. And what it seemed to be that if we got early enough access to these people, we could actually influence the progression of the disease, which I found interesting. Since that time, and when I was in medical school, I became the laser research coordinator for a sub-college called the Einstein Medical Institute. And I did that up until about a year ago. I also was doing a lot of research in nanocarbon medicine. I don't know if people are familiar with C60 or with carbon nanoonions. I've published, I think, 7 papers, peer-reviewed journals on that. And from that, that research began to become aware that maybe there might be something more that we could offer doing lasers. Because, I mean, frankly, which we'll get into the presentation, is there's not a real consensus on what we're doing. We know there are certain biochemical effects in the body, but we don't have a hard, fast concept on what we're doing, or even how to maximize it, because the studies are all over the place.
I agree.
So
it brings us to the topic of your expertise. Let's go to the slides.
okay.
Resonant harmonic frequencies, effects of near-infrared photostimulation on cellular communication and self-organizations, quantum considerations. Take it away, Dan.
Okay. As I said, this is going to be basically looking at harmonic frequencies, its use in near-infrared photobiostimulation. And we're going to focus a little bit more on quantum considerations rather than what we call Newtonian physics, which is what current biology is currently based on. So today we'll end up discussing the quantum view of electromagnetic influence on intermolecular interactions in living systems, eigenfrequencies, which eigen basically natural frequencies, and harmonic resonance in biological systems, and then applying these eigenfrequency based harmonics for laser therapeutics. As I mentioned in the intro, we're slowly gaining in understanding of many of the biological effects of photobiostimulation, but there's no consensus. And I think this hinders the acceptance and also the effectiveness and clinical implementation of laser therapeutics. We can't agree on whether high power lasers or low power lasers or even non-coherent LEDs are effective or should be the method of choice. The fact that we can't get a consensus means or suggests to me that maybe we're asking the wrong questions. And the question I think we need to look at involves being able to affect the body's harmonics or the natural frequencies that are occurring in the body.
So that means that there's no adequate explanation as to how light instruments which lack the power to physically penetrate and deliver sufficient photon energy to target tissues produces the known biological effects of PBM. The continued lack of demonstrable consensus suggests that we've been asking the wrong questions.
Yes, and in your question, which is what I think a lot of clinicians and researchers actually are seeming to miss, is that biological systems, there's no independent events. Intermolecular actions are part of a system, and they affect every other part of the system on what's going on. And if they are not closely coordinated, the whole quantum critical biochemistry would collapse. Ions and electrons and molecules can't do their own thing. They have to be coordinated, and they have to be, the system has to have a way to do that. One of the ways they do it, there's a paper in the bibliography section at the end, and I'll mention it a little bit later, Bischoff and Degaitis, as well as his name escapes me right now, but he has a paper on the biological water, and that will shed a lot of light for people, get you thinking a little bit different on whatever you're seeing happen or being reported in various papers when any type of therapeutic device or molecule or medication is applied in the body. we want to get back to our slides here. The electromagnetic frequencies, biological influence, it depends on the frequency of the field. Bourassa pointed this out, that it's been established that the influence of external electromagnetic fields on living system depends on the frequency of the field. It has been shown that certain frequencies has biological effects that are non-thermal, and moreover, in many cases, the weaker the field, the stronger the effects, which has been an argument of the LED community and the class 1 and class 3B lasers, that they are affecting biological
Maybe.
systems.
The biological field of the organism and not the
Right.
tissue itself.
Yeah, these two experimental facts establish the resonant character of the influence of electromagnetic frequencies on biological systems. It is known from theory that photons, an oscillating electromagnetic frequency, has two components: a magnetic and an electronic or electric field. And they're hooked together by the Maxwell equation, and that's not important. But it's important that we distinguish the effects of the two. And most people are probably a little bit more aware of the effects of the electric component, which can affect the organism on the level of the skin at biologically active points, such as photon or laser acupuncture, or at some depth, depending upon the frequency of the field. And the reason is because biological matter contains a significant amount of water, both intracellularly and extracellularly, and this can absorb a lot of the electrical radiation effects. I think in some of the frequencies that we're using, obviously, as we get closer to the infrared range, we're going to have a tremendous effect absorption by water. The magnetic component, on the other hand, is much weaker than the electric component. And however, especially at low frequencies, can affect biological systems because tissues are macroscopically non-magnetic, and the field component can penetrate very deeply into tissues to cause local effects deep inside an organism.
I see what this is doing when you take a very low powered device and it oscillates. The tissue underneath it will sort of oscillate similar way, and this is what you're calling not so much is that the electrical component, or is that more the magnetic component?
Well, I think it depends on where you're applying it and how it's going. There's, like I said, there's still a lot of research that needs to be done, and part of the reason for my presentation is to get the researchers and people that read this thinking in this direction. There's a lot of questions that I don't have answers for. I'm just presenting what the literature has revealed and what I have noted, clinically to some extent.
Got it.
But so did I get this next one? But basically, I'm trying to stimulate people think in this direction so that we can get research and answer some of these questions for everybody.
Got it.
The electric and magnetic fields, and there's a picture of electromagnetic wave of the photon. The cell sustained by biochemical reactions, which involve electron transfer, while cell functions are generally involved by membrane components and involve ions. And light interacts with the biomolecules with electric fields, causing electric cloud to oscillate, such as those with ring structures. There means in order for there to be an interaction, the electron cloud must move. That's one of the things that Carew talks about with the cytochrome C COX enzyme in the electron transport chain. But light can also be absorbed via a magnetic component and interact with the cellular magnetic fields and biomembranes, the interfacial water, and the molecules, as well as the ring structures. Mentioned the carbon-containing ring structure. They do play an important role in energy production in organisms, and photons can, through their electric and their magnetic field, can affect this. When electrons move inside a ring in one direction, a magnetic field perpendicular to the ring is created. If the direction changes, an alternating magnetic field forms, and then this can form a magnetic scalar wave. I don't know how much many of the audience are familiar with scalar wave therapy, but it's basically a standing wave, and it's going to have a resonant frequency since it is a wave. Again, people read that reversely. If an oscillating field scalar impacts a ring perpendicular to the plane, it acts as a generator to put an electron in motion. And if no external force is present, electrons will remain in that direction. So the ring assumes a duty as an energy source, an energy sink, as well as a storage for the field of energy.
Huh. There we are.
And this next slide is just from there showing how many magnetic waves enable cell communication. The next one, non-thermal resonant effects resulting in photo-induced magnetic fields may provide an alternate explanation processes of for redox processes and energy production, as well as metabolism of the organism. Now, this is kind of the geek stuff, so I'll try not to spend too much time. People can go back and look at. I think you were going to provide a PDF of this or the PowerPoint, and it'll go a little bit more detail. Plus, the papers in the bibliography also have go into depth. But anyways, solitons and polarons drive biochemistry in living organisms, and so. And the soliton model of charge and energy transport is used to suggest one of the possible mechanisms for electromagnetic radiation's influence in biomedical systems. Electromagnetic frequencies resonate with the solitons and bisolitons, and I'm going to cover what a soliton and a polaron are, and all of a sudden this will kind of come together for some people. Brisnick and others noted that the external electromagnetic field can influence the solitons in living systems, and electromagnetic frequencies that resonate with the solitons bisolitons drive the charge transport along the electron transport chain redox processes, driving the Krebs cycle and oxidative phosphorylation. Also in photo phosphorylation, also in plants. The propagation of charged solitons along a polypeptide chain is accompanied by the radiation of electromagnetic waves in the form of a superposition of harmonics with multiple frequencies coherent with the frequency of the overriding or regulating quantum electrodynamic field, which is really a phase of the system.
So the current
kind of like a standing wave.
That's in the system. That's kind of the resonance of what that system is doing.
That's the overriding that's the connection between every biochemical action and molecule, ion, atom inside the body. That's influencing, that field is influencing how it interacts with every other particle. Okay, so I said we'd tell you what a polaron is. Polaron is a conduction electron or hole together with self-induced polarization in a semiconductor or ionic crystal, which forms a quasi-particle in quantum physics. And it describes the physical properties of charge carriers in polarized solids, i.e. proteins, but also because it constitutes an interesting field theoretical model consisting of a fermion, which is an electron, with a scalar boson, which is a photon. Didn't know your photons were bosons, right?
No, I didn't know that, right?
Okay, so a soliton is a self-reinforcing wave packet that maintains its shape while it propagates at a constant velocity. It does not propagate in a vacuum such as light does. It has to propagate in a medium. And they can interact with other solitons, but they don't change from this collision or interaction, except for possible phase shifts. And in fact, solitons actually will become multiples and become actually stronger, much like if you notice in music, when you play a note and you play its harmonic note, the sound is a lot louder. That's the similar type of thing that would go on with two in phase vibrating solitons. And these multiple solons obviously have mass that's squared, it's not added, so it's not proportional in that sense. Those are not very important to the clinician, but it does help if you're going to be doing research in this and understanding some of that stuff. Solitons and peptides, such as electron transport complexes, are a particular case where large polarons, we talked about these electrons and electron holes, represent the crossover between small polarons and almost free electrons. And they correspond to the ground electron state at the lowest energy. Nature always seeks the lowest energy possible in all its biological activities, unless it gets stimulated, forced to a higher level, but then it quickly wants to return to the lower level. And this involves a electron lattice coupling. And so we'll get to that here in this next one. All right, so there's at least 3 physical mechanisms of biological effects on magnetic fields that can be identified. And they're molecular, supramolecular, and system. And it depends on the level of organization at which such effects take place. Now, you can read this too, but molecular mechanisms, they affect the ions, radicals, paramagnetic particles with unpaired electrons and spin, molecules, macromolecules, and they can induce the spin singlet triplet transitions in molecules and changing their states. So that would be one of the things where a photon interacts, say, with the ring structure in the COX enzyme. Supramolecular mechanisms involve the effects on the membranes, mitochondria as a whole, microcrystals, cell nuclei, and the biomolecular structures, which are all hydrated, and which are hydrated by what's called interfacial water. And interfacial water has interesting characteristics because it promotes electron and proton tunneling, charge transfer, absorbing and storing, transferring, emitting electromagnetic energy and information. But the system mechanisms are much more complex, and they're actually delayed because they are a result of the first two, the molecular and supramolecular mechanisms, which produce effects on the corresponding system or whole organism. So we'll get a little bit more of the geek stuff, and then we'll get on to the practical application. Dependence of biological effects of oscillating magnetic fields on the frequency indicate the resonant character, and they consist of the ion cyclotron resonance, electron cyclotron resonance, and a molecular cyclotron resonance. The ion cyclotron resonance in biological systems, where there are various ions and groups of ions which are sensitive to alternating magnetic fields. Electromagnetic oscillating signal of a frequency will therefore resonate with ions which move along a circular trajectory with an angular frequency. In a more general case, this actually forms an axial motion, resulting in a helix or more complex trajectory. If people are familiar with toroids and toroid fields, that's where we get some of that. Okay, the ion cyclotron. Wait a minute, where's my next?
This is ion, this is the electron.
Ion cyclotron resonance. I can't change it, so
You're watching me.
Change it. All right, so the electron spin can be influenced by internal and external magnetic field resonance. And some molecules in electron transport chains, like quinones and cytochrome C, they're relatively small molecules, and they're mobile, and they can transport that electron from two larger molecules, on the normal chain. That's the way we usually think how things, or it's very similar to how we describe how things go in electron transport chain. Molecular cyclotron resonance, larger molecules in electron transport chain, such as the NADH ubiquinone, oxygen reductase, the flavoproteins, the cytochrome C oxidase, site 3 cytochrome C, the BC1 complex attached to cytochrome C oxidase. It's a different situation because the electron transfer of these proteins, which have an alpha helical conformation that's stabilized by relatively soft or weak hydrogen bonds, and they're between every 4 peptide group. So along the helix, there's 3 hydrogen bonded peptide chains, resulting in a strong electron lattice interaction amongst them.
Such deformations act as potential well.
Acts as a potential well, which attracts the electrons. And as a result, a bound state of electron and lattice deformation is formed. The electron lattice results in self-trapping of electrons transferred into the protein, creating deformation of the protein. A bound state of the electron and deformation is formed, which propagates as a soliton or bisoliton. The bisoliton represents 2 extra electrons with antiparallel spins that are localized within the same deformation. The effective mass is bigger, as we mentioned earlier. And, so in summary, there is a resonant effect of magnetic fields on the dynamics of solitons, and hence on charge transport that accompanies photosynthesis and respiration. These effects result in the non-thermal resonant effects of magnetic fields on redox processes in particular, and on the metabolism of the organism. The electron and lattice deformation propagate along the peptide chain with a constant velocity from one end to the other, and from a donor to an acceptor molecule as a coherent localized wave. Obviously, whenever we see the word wave, what we should be thinking of, well, that wave has a frequency. And those are the frequencies that, excuse me, that make up these eigenfrequencies. So electromagnetic fields of weak intensity in the broad interval frequency intensities can cause various biological effects, and these can be positive or negative, depends on whether or not they resonate or interfere with the harmonics of the organism. Okay, so at the eigenfrequencies, at the most elemental level, all matter is in constant motion, and as I mentioned, eigenfrequencies or natural frequencies are certain discrete frequencies of the system and its subcomponents, and they are naturally prone to vibrate in unison. Okay, Bishop and Delgaitis note that the quantum critical intermolecular interactions in living systems occur as a collective array of interconnected events. And they conceptualize an organization, structure, and biochemistry is initiated, maintained, and regulated in a domain-like fashion by a coherent phase correlated standing wave, or EM potential. And this phase vibrates at certain frequencies, and subsequent frequencies coherently resonate with this phase. Okay. Additionally, the phase can be trapped, maintained in the coherent domains of interfacial biological water, and that hydrates all structures. There's nothing inside living systems that aren't hydrated. That's actually how things work. Nature makes use of specific eigenfrequencies, and you can read this paper if you want to do some of the work. That's what I had to do. One of the things that took me a little time, but these resonate with the little cellular structures, the antennas, so to speak, like the ring structures, and then the coherent domains in the interfacial water layers, as well as plasma channel and tubular proteins in the cell. They all absorb and they can emit quantum wave information. So the basis for this was research by a couple of guys, Mayer and Gising, and they conducted an analysis of more than 500 biomedical publications that reported life-sustaining as well as life-decaying electromagnetic frequency as a result of exposure to the external radiations. Because even if we weren't doing this or we weren't being exposed to external radiations, we would still have this process going on within us. But we're concerned with external radiation effects. Okay, so what they found that these frequencies also correspond to the generalized musical scale, which is an acoustic algorithm of 12 tones that describe electromagnetic frequencies in band patterns that have beneficial or detrimental effects on living systems. Think about, many people are aware of like sacred sounds. Certain sounds can do certain things. We know that classical music, which is in frequency of 432 hertz, has tremendous benefit in Alzheimer's patients. So there is basis for all this that we're talking about, these eigen frequencies, and what we need to figure out is how to take advantage of it. So let's see, this next one here are observed electromagnetic effects, and you can see there's a bunch of things that happen in the brain and nervous system. Positively side, if you hit the right thing, neurostimulation, brain stimulation, spinal cord stimulation, transcranial magnetic stimulation, treatment of Parkinson's. We also have improvement of memory function, conscious attention. One of the things that I use in my studies is to use it to stimulate improved focus, conscious, and memory in going through a lot of the research in, I was working on my PhD as well as in medical school. It also affects like promoting entorhinal and hippocampal interactions. All those things are beneficial. Then on the other side, of course, people can read that. You can see where you can impair cognitive impairment if it's the wrong destabilizing electromagnetic field frequency, or
right. If it's going to be, if you're in the rhythm or you're out of the rhythm is basically what you're pointing out here, you know, so that you're begging the question. All right, so what are the frequencies? And here we are. Go for it.
Right. Okay. So here is those 12 harmonic. This is a GMS scale that they came up with. Now you can see the red here. Those are detrimental, or what they want to say, decoherent frequencies to the natural biological field. And the green, obviously, are beneficial, right?
Right.
A little later, I'm going to show you where our lasers fall on the scale, because you can't say, well, I don't see 800 on there, or I don't see 650 or 980, 1064. Well, first off, these frequencies are in hertz, and
right,
you can't convert 810. It's not 810 nanometers. Can't be converted into 810 hertz. It's something like 3.7 times 10 to the minus 14th, or basically 370 terahertz. Okay, got that. So, all right, I'm gonna have to
coherent. These are the quantum biosystems 2019. These are either coherent or incoherent frequencies, you're saying, based on these different.
What I have this up for is this has been some research that's done on certain molecules in the body. Okay, and this is done. These things are done in vitro. So anytime you do anything in vitro, now you no longer have that overriding quantum electrodynamic field. So, but it does give you an idea that these light frequencies or electromagnetic frequencies have interact with certain biological molecules, and you can see they can be negative or positive. Okay, this is some of the work that they've done. Here's the next one. It's just a continuation of that. Okay, so you can see in there, I'm just showing this for reference. Okay, now here is a lot of the biological detrimental effects in hertz.
Right, we're at the pulse laser light now.
Right.
In spite of the fact of relative long history of using pulsated radio frequency, magnetic fields, and lasers in medicine, little is known about the mechanisms of such therapies. Most research into various pulsing frequencies has been done in the radio frequency and magnetic resonance therapy scenarios.
Okay, see, you're down a couple slides ahead. Those other slides just show the various things that people can look at compared to their particular lasers, because it was done with that. Okay, yes.
So we're at the near infrared photostimulation based pulsing research has been very limited to date. This research has also failed to identify well-defined pulse frequencies for specific therapeutic benefits. I think you're absolutely correct here. However, the consequence is that pulsed near-infrared laser light, whether it's superpulsed or pulsed, and you use the term chopped or gated, offered greater benefit than continuous wave light therapies in some conditions and in some parameters, right? Pulse laser-based transcranial photobiomodulation is one area that pulsing, but specifically 10 hertz and 40 hertz, whatever, has frequently been shown to have some significant benefits or greater benefits than constant wave. And that really, there's so many parameters when you start talking pulsing, and you're giving us some reasons why. At the greater range of effective pulse frequencies and perhaps narrow specific frequency selections for specific conditions and therapeutic applications. I think that you're going after the holy grail, Dan, because I always said, I'm a constant wave dude. I don't pulse the stuff, because I said, if someone told me there was some evidence that this frequency of pulsing does this, then I would say, yeah, I'm into that. But there's no angels whispering to me, and you're going into the literature right here. So let's see what they say. Laser applications.
Okay, all right. I guess we don't, in the interest of time, we won't read the obvious slides, but laser light spectrum we need to look at, and
pulsing frequency. There we are.
Frustrating it is to you, pulsing frequency, and we need to figure some of this out, because pulsing is, I think, has some potential simply from the fact that, understand, look, a lot of biological systems respond very positively to certain terahertz frequencies, but the higher you go up in hertz, okay, the less tolerant the body is of the wrong frequencies. You have a greater ability of the body to deal with lower hertz frequencies when it comes to the eigenfrequencies, coherency and decoherency. So therefore, I think the pulsing range is very positive, maybe up through a couple kilohertz. Okay,
so
let me where our lasers fall, Joe.
Okay. Yep.
Okay. I believe you like using 632. Is that what you do?
I'm around there, 635. Yep. 660. Okay. I'm down there. You can see that there's a lot more.
You got it nailed. The other one that nails it is 1064. However, 810, 808 is right there on the line in the eigenfrequencies. Okay.
Let me just ask a question here, because this is the frequency of the wave. The nanometer is the frequency of the wave, and not a frequency of the on and off. Am I correct in understanding that? This
is your laser's coherent frequency, or it should be centered on that. Depends on the quality of your laser diode, right?
Mm-hmm. And it completely makes sense, because if you do, they've shown, like just recently, the other speakers, if you do 780 nanometers, it really doesn't do anything. And maybe it does something bad, right? But if you just go 810, it seems to do something positive, right? And I think that you're really focusing in on the real good stuff of the nanometers of wavelength of light, and has a beneficial effect on the system as a whole, and then probably down as you're going to describe it down to the specific, we have systems, molecular and ionic type of things, right?
Yes. But now, not to make it more confusing for some people, but 980 seems to have some beneficial effects, especially in pain attenuation. Now, question is they're speculating on what is it doing, but it may actually be impairing some of the processes that and the enzymes or molecules that are contributing to inflammation. It may actually be impairing their function. So that's going to affect the development of inflammation. Additionally, there's such a thing as hormesis. That's where you stress the system a little bit, but not too much. And the body then compensates to become stronger to resist against it. That's what we do when we go lift weights or when we train for an athletic event. We build on it, and the body has to build on it. The same thing with our immune system. It's a hormetic event. You insult it, and then the body responds by compensating and making it stronger. So there may be some effects from that, and that may be a valid therapeutic goal. Okay, that's the point here, is we need to understand how this is interacting. Now, you can see there, if you were pulsing, say at 432, okay, you would be synergistic, because 432 hertz would be very harmonic with your 632 nanometer laser. Do you see what I'm saying?
That's very in depth, because what's going on is that as the pulsing of the frequencies of the little square numbers there go down, the nanometers go up. So you're looking at, that's kind of important too, right? Because if most people aren't pulsing at these, you're looking at pulsing at 432 hertz for the red light, like you're saying, and then lower for the infrared light. So it's be pulsing, let's say for the 1064, 256. So if people are pulsing it, and there's people that do pulse at that, but they're using the wrong infrared. So you're not.
That's not exactly what I'm saying. What I'm saying is if you have that 1064 laser that you mentioned, if you pulsed it at 324 or 432 or at 256 or 384, that would be an in-phase harmonic. These harmonics, these green things, are all harmonic together. Those are scales. When you play music, think of music, and if you have you're playing the note, but it's tuned to a different frequency, it's the same note. It's an A in 432 or 440. All the music nowadays is very decoherent to people, and it probably caused some problems. They shifted from 432, which was the frequency of classical music, all the way back to Pythagorean and the Greeks. They started realizing these frequencies had beneficial values and were enjoyment, relaxed people, and did this, that, and the other thing. Well, sometime in, 20s or 30s, all of a sudden they determined that they're going to go to the 440, and now modern music is generally in the 440 harmonic scale, which you can see clearly. 440 is not in a good spot there.
So if I understand you, then you're saying that they're sort of, you could pulse a red light at the sort of quote unquote green frequencies, and it's sort of going to do the same thing. Am I understanding you properly? Because it's sort of the same thing.
Yes, but I'm said this is for therapeutic application for people to do. So if we move down, you're going to see that we don't have to use 432. You could, okay. If you go to the next slide, these condensate, we call it condensate frequencies, but these are all harmonic frequencies. Now, I don't have a laser. I can get pulse in 1 hertz increments up to I think 2,000 kilohertz, basically 2 kilohertz. But you can see 4. You can pulse it at 4. You can pulse it at 6. Pulse it at 64, 72, 96. And I've used these different frequencies, and it seems to have some pretty beneficial effects. And of course, this 255 to 487 hertz are those eigenfrequencies that showed up on that scale that we looked at. Okay, but you can see you can get up into in the kilohertz range, and I don't know if you, I guess you could be able to, depends on as we go up in the lasers, a lot of times they won't let you do it in actual single hertz range. When you get above, say, 1,000, it may go by hundreds and things like that. So notice none of those are even. You can come close here at the gigahertz, but you're not putting out enough pulsing availability, either chopped or gated. The question is on the 904, you obviously would want to come close to that super pulsing at a rate and an eigenfrequency to enhance the 904 effects. Okay, let's go to the next slide.
This is the eigencompatibility pulsing grid.
Okay, so what I did is I broke down all those frequencies into some usable for many lasers that are on, at least the class 4 lasers. And you can see if you're going to pulse whatever frequency your laser is, you probably want to do the green. You can come close with the red frequencies, okay, because these are rounded slightly to the next higher number. And like I said, the lower hertz are tolerated a lot better. However, this is where we need to start the research and find out which one of these things work in which conditions. We don't know. They're going to be a little different. But if you enhance the eigenfrequencies or the phase frequency, if you build on that, you're going to have a healthier system. To the extent that your eigenfrequency or your system is losing energy, that's a sign of disease. That's when enzymes and proteins and other things in the body don't work well, and organ systems don't work well. So what we want to do is enhance the body's quantum molecular dynamic field and the subsystem frequencies with harmonically compatible frequencies. And I think we can investigate that in lasers. And if you have lasers that do that. Okay. Basically, if you go to the next slide, point that out, because most clinicians don't know the specifications of their lasers and their light equipment. Okay, you're going to you rely on preset treatment parameters provided by the particular manufacturer. As I said, back in 2010, basically showed the manufacturer had his head up spot. And to make matters worse, after I showed them, their medical advisor attempted to do the same thing and didn't come close to doing what we achieved. However, they never did alter their recommendations to doctors. So
I'm with you. I'm with you. And this is your frequency matters in biological systems. I mean, I just want to turn back to the compatibility pulsing guide for 1 second here, just so that I'm clear, because if I understand, we went from wavelength to just frequency, which these are the good frequencies. And then we kind of looked at what the pulsing would be in green for these different beneficial resonant frequencies. Am I following you there? So if I'm making any sense, some of these lower pulsings.
Go back one more slide.
This one.
To this, okay? All right. These, look on the yellow listed down the side. These are the terahertz frequencies That's the hertz that you're actually delivering. You see that?
With that wavelength of light. I
Right.
got
People
you.
are confused because we're talking nanometers and then we're talking hertz. But my point is, you are delivering these. This is a beneficial eigenfrequency or compatible eigenfrequency right here.
Mm.
Okay.
Well, the thing is that hertz is not terahertz.
No, it is. This is in terahertz because otherwise, if you wanted to put, it would be 4.74 times 10 to the 14th. Big number. We don't have enough room here, so we're just going to call it terahertz.
And that one, then, how does that equate to when you're breaking it down to this thing?
So this is the pulsing. We have the lasers that we have. I have an 810 980. Okay. I use 810, and if I'm using the brain, I don't use.
No. It's me.